Okay, here we are in a brand new video, and we got some really exciting things going on here. It's about what's on the left, and it's a diagram out of a textbook. 1926 is when it was published. It's Mathematics for Engineers, and it was by Raymond and Robert Dull, or by Dull and Dull, and it was published by McGraw-Hill. I represent that the only thing they said about this diagram wasn't very much. They said that it was so self-explanatory it didn't need any more explanation. Then the other thing they said was that it was, back then, in 1926, it was used as a engineering drafting aid. And they suggested that if you put this diagram to scale, that you could use a pair of dividers to transcribe accurately measured line segment values and the square of that line segment value. In other words, B is a line segment length, then the blue line here would be the exact square or second power of that same length. That's all they said about it. I took one look at it, and what I saw was an excellent opportunity to see a basis for a proof for the Pythagorean Theorem, the kind of which I've never seen before. If you look at it, this is inscribed inside of a unit circle. It uses a technique of similar triangles in order to be able to come up with the symbolism on this diagram. But in this diagram, the hypotenuse has a length of 1. I've seen similar triangle approaches for Pythagorean Theorem, and if you don't use c equals 1, then you won't get this result. But anybody else who uses c equals 1 will get this exact same result. All I did with this diagram is to mathematically model the diagram to be interactive for intuitional purposes. Let's see what that looks like. Here's a control for the angle. Okay, so you see the angle is moved. Okay. Now, before I move on to the proof, there's something very important to point out here as an aside. They've done something with that I've never seen before, which I'm adopting for my own purposes from now on with mathematics, and that's the use of symbolic values. In other words, not numeric values. In other words, this symbolic value for A here represents the measured distance across this line segment, and that's the way they use symbolic values in this whole diagram. And the neat thing about it is that when you do that, the power can be seen. Power behind that technique can be seen, because at a glance you can see when line segments have a relationship. This is a to the first power, and this is a to the second power. So anyway, I thought that was pretty neat. This one is a quantity of b to the first power for this length of this line segment, and this one has a length of b to the second power for the length of this line segment. Okay, so moving on. I'm gonna go full screen over here, and I'm gonna represent that the act of putting in this line segment right here. Well, first of all, before I do that, as an aside, this line segment could be thought of as a altitude with respect, of course. If you chose the hypotenuse here as the base of this triangle, then they would make this line segment an altitude with respect to that hypotenuse, as if you selected that hypotenuse as the base of that triangle. Now, two things very interesting have happened here by the act of doing that. We've got two more triangles, and I represent that they're equal, similar triangles. In other words, by virtue of the fact that they all have the same angles. So let's see what that looks like. If we put theta here, and this is 90 degrees, that would make this 90 minus theta, and that would make this theta, and that would make this 90 minus theta because there's 90 there. Okay, so the other thing that's happening very interesting here is take a look at this side. In this largest triangle, it's the opposite side. In this triangle over here, it's the hypotenuse. Okay, so moving on. Over here, we see that these two triangles are similar, and as such, in geometry, the ratios of corresponding sides is equal. Okay, so let's examine the ratio of opposite sides to hypotenuse for the large triangle, and the same ratio for smallest triangle. We'll look at that right up here. For the smallest side, the opposite is E and the hypotenuse is B. So we see that right here, E over B. Okay, so let's examine the opposite side over the hypotenuse for the large triangle. And we're going to see that over here. The opposite side is B, and the hypotenuse is 1. Okay, so B over 1. So we see that these two ratios are supposed to be are equal. So and the interesting thing about it here in terms of this framework here, we can see that B was playing the role of opposite side for the large triangle. Now it's reversed its role. This same side is reversed its role to be a hypotenuse for this other smaller triangle, and that's what's caused this to generate a second power squared term. In the other cross, we have 1 times E. 1 times E is equal to B squared. That's the reason why I can write E equals B squared here and repeat that over here. E equals B squared. Okay, so moving on. The same interesting thing has happened with this blue color-coded line segment. Here in this largest triangle, it's playing the role of adjacent side. Okay, moving on. Down here for this medium triangle, this exact same side is now reversed its role, and it's playing the role of hypotenuse. Okay, so for examining the relationship or ratio of adjacent sides to hypotenuse for the large triangle and adjacent side to hypotenuse for the medium-sized triangle, let's see what that looks up here. For the large triangle, the adjacent side is here, and the hypotenuse is 1. So it'd be A over 1, and that's what so that we have that right here, A over 1. For the medium-sized triangle, we're going to examine the same ratio, adjacent side over hypotenuse. Here's the medium-sized triangle, and here's the adjacent side of this, which we've got labeled as D. So D over A, and we've got that right here, D over A. So in this framework, we see again that this side A, who was an adjacent side, has reversed its role to become a hypotenuse on this medium-sized triangle. So that's how we get a squared term here, A squared equals D. This cross multiply would be D, 1 times D. That's how come we could write D equals A squared. D equals A squared. So quite literally, the quantity A squared plus B squared is equal to C squared. And here what we have is two terms of the Pythagorean theorem. This is the first term of the Pythagorean theorem. This is the second term of the Pythagorean theorem. And these two don't have anything to do with areas. These are scalar lengths. So this scalar quantity plus this scalar quantity is equal to this scalar quantity of 1. Anyway, that's the end of this video. Please like and please subscribe. And have a good day. Thank you.